Okay, how's it going, guys? Today we're going to start chapter 13, talking about liquids and solids. Mainly liquids. We don't really focus too much on the solid aspect, solid state of matter here. We really focus on the liquids and the explanation for, again, why liquids do what they do, why they behave certain ways, and the different properties of liquids. So one of the biggest things this chapter is intermolecular forces, which we'll get started on in just a moment. A couple of general things to take note. Sorry, that was my phone, which was right nearby, and I haven't quite figured out how to delete the last few seconds. Anyway, no biggie. All right. So as I was saying, a few things to take note, right? Differences between solids, liquids, and gases. So you guys want to be familiar with general differences in the states. So basically what I'm talking about here is the simple things that you guys learned in your first year chem class. Heck, is probably stuff you learned in middle school. Understand that, gases, they expand to fill their volume. Liquids and solids don't. Liquids only take up the amount of volume that they exist. Solids retain their shape. Solid molecules are really, really close together. Liquids are also very close together, not quite as close as solids, but just a little bit further apart. And of course, gases are really, really spread out. And then, of course, gases are compressible, liquids are virtually incompressible, and solids are virtually incompressible as well. We know gases diffuse pretty fast through other gases. Liquids diffuse within other liquids very, very slowly, and solids diffuse through other solids extremely slowly. Okay, so just kind of some general points. Again, most of the stuff you guys are familiar with, just to be able to discuss the differences and picture the differences at the molecular level between solid, liquid, and gas. Okay, good general statement here. Difference, right? What state of matter a substance is in depends on two things. So it depends largely on these two things in balance. The two things are the kinetic energy of the molecules kinetic energy of the particles. So atoms, molecules, compounds, etc. And it depends on the interparticle energy, or I should say energies, of attraction. Alright, so it's kind of a loaded statement. But it's good to keep this in mind. So what state a substance is in? We tend to only associate it with the temperature, right? Because we're so familiar with water, we tend to always go back to water. We know that water is a solid below 0 degrees Celsius. We know it's a liquid from 0 to 100, and we know it's a gas above 100, right? And so all those temperatures are great at 1 atm of pressure. But again, get back to what temperature means. It's a kinetic energy, right? It's an average kinetic energy. So what state of substance is a balance between not only just the kinetic energy, which is how how much energy is within each molecule, how much are they vibrating or moving, but it also has to do with the forces of attraction between each particle. Okay, very, very weak forces tend to exist in gases. Very, very strong forces tend to exist in solids, and of course liquids are somewhere in between. So we're going to go through those forces. We call them intermolecular forces, which we're going to get to here right now. Okay, with intermolecular forces, we have a series of them. I'm going to kind of go in order from strongest to weakest. So So we have your intermolecular forces. Of all the things this chapter hits, it's these, and this is probably the most important because we use them to describe a lot about molecules. So a couple of general things. An intermolecular force is the force between molecules. So not any sort of attraction or force inside of a molecule. It's always the attraction between two or more molecules, of course. And these forces are all based on electrostatic attractions. Fancy word just meaning it has to do with the positive and negative charges within molecules. So, some of you might be thinking, polarity. Yes, of course, polarity plays a huge part in understanding intermolecular forces. And I just realized I did not spell forces right. I forgot the C. Okay, alright, anyway. I know somebody probably mentioned that, but I noticed it. Makes me wonder about misspelling other things. Okay, anyway. Polarity is a huge part, so you got to be familiar with polarity. If you go back and look at your Chapter 9 notes and material and how to figure out if something is polar or not, that would be good. Because polarity does, like I said, play a very major factor. And we start to actually categorize and determine in easier ways, hey, what molecules will be more polar, which molecules will be less polar, things like that. So we just kind of expand on the polarity idea. Having a good base of that is incredibly important. Okay. First intermolecular force. I'm going to title this in a different color here. We have what we call ion-dipole attractions. Okay. So we're kind of dealing with so again, intermolecular force always has to be between two things, right? So here the two things are undo that. I meant to have my arrow. The two things are the ion, okay, remember an atom with a charge, and dipole, which is just another word meaning polarity. So you have a polar molecule and an ion. That results in a pretty strong attraction. Okay, let's jot down some ideas. So remember dipole, another word for polarity. So dipole molecules have inside of them positive and negative ends, right? That's our definition for polarity. Imbalance of charge within a molecule, a positive end and a negative end. So here you have, you're dealing with an ionic compound. Ionic compounds are made up of ions. They have full-on positive and negative charges, right? So naturally, you have an ion mixed with a polar molecule. A positive ion is going to be attracted. So a positive ion here is going to be attracted to the negative end of a polar molecule. Likewise, negative anions will be attracted to the positive end of a polar molecule. And that attraction we call an ion-dipole attraction. Not a fancy name, I know. This attraction depends on two things. Well, no, it actually depends on three things. But two of them, well, actually all of them you're familiar with. That's kind of nice. So similar to how we described the attraction between ions, we have to consider the distance between ions and the dipole molecule. Right? So remember the idea that the closer you are, the greater the attraction. Right? And so to judge that, you have to look at the size of the ion involved. Right? Are you talking about a large atomic radius or a small atomic radius? Small atomic radius always leads to greater forces between ions and between molecules because they're smaller. And the nuclei are closer together, greater force. The bigger you are, the smaller your force is. Okay? The other thing, maybe some of you are predicting it, is the charge of the ion. This was the easy one. The bigger the charge on the ion, the bigger the force. So a positive 1 ion will have a smaller force than a positive 2 ion. Or if those are negative, doesn't matter. Either way, the bigger the charge, the bigger the force. The other thing you have to consider is the magnitude of the dipole. So this kind of deals with, is it a more polar molecule or a less polar molecule? And remember, the more polar you are, the greater your electronegativity difference. Okay, when your electronegativity differences are very, very small, that's not a very polar molecule. Your electronegativities are huge, that leads to a very polar molecule. So if you have a very polar molecule mixed with a highly charged ion, that creates a very, very strong force of attraction. On the opposite end of the spectrum, if your charge is very, very small, and let's say your ion is huge, okay, and your polar molecule is not that polar, well, guess what? That force of attraction is very, very small. We can kind of draw, I'll do my best to draw an example of what we're talking about here for ion dipole attraction. Let's kind of look at a polar molecule. H2O is a good example. So here we have our H2O molecule. Remember, it's a bent structure with lone pairs. Our hydrogens have partial positive charges on them. Remember, that's a Greek letter delta. And this is a partial negative charge on our oxygen, right? So that's a polar molecule. That's actually a very, very polar molecule. And let's say you dumped in something like an ionic compound, lithium bromide. Lithium bromide is an ionic compound. Dumping into water, it dissolves. Well, guess what? Our bromine atoms, which are actually quite large, our bromine ions, I should say, are Br minuses. This has a total negative charge. Our Br minuses will be highly attracted to the hydrogen ends of the water molecule, and our significantly smaller, let's see if I can fit it in there, that says Li, our smaller lithium ions, which are positive, are attracted to the negative oxygen end. Okay? So the forces between these two substances, the forces in between, I really don't like how I drew those. I just kind of wanted to draw like little dots. Okay? That's our attractive force. Okay? Our forces here, here, and here. That's our ion dipole attraction. That's the intermolecular force. And that's a pretty strong one. Okay? So that's kind of our strongest intermolecular force. This one actually doesn't come up all that often because it's kind of a mix of an ionic compound and a liquid. Okay? And so most ionic compounds are solids, so you're kind of putting together a soluble solid with some type of a polar liquid. Okay, the next ones that we have coming up are much more common. So I'm going to start a new page. Okay, next intermolecular force is known as a dipole attraction. A dipole attraction deals with two polar molecules. Or a dipole attraction is between two polar molecules. And they are each attracted to the other, to each other's opposite end. Pretty sure there's supposed to be an apostrophe on others. I really don't know where it's going to go. So guess what? I'm going to leave it off. You guys can put it wherever you want to. Okay, so dipole. The word is said twice because you're dealing with having at least two polar molecules. All right, so we know that a dipole is just another word meaning polar, molecule's polar, so it has a positive end and a negative end. So if that's near another polar molecule, well, the positive end of one polar molecule will be attracted to the negative end of another polar molecule, and so on and so forth, just like a whole bunch of series of little teeny tiny magnets, all being attracted to each other. This could mean, the two polar molecules could mean two different polar molecules, but most of the time it just means they're all the same, right? So take any polar molecule, for example. You never just have one single molecule, right? You have trillions of them. They're all near each other. So if you just have you have a polar substance, then it's a dipole attraction. One easy way to compare the strength of this is to look at boiling points. So we can compare this force if we look at the evaporation and condensation of liquids. So this is kind of going back to a little bit of our vocabulary from chapter 6. If we can look at the delta H of vaporization. I'll write out the whole word here. And we can compare the delta H of condensation. Right? Vaporization, condensation are opposites, right? Going from liquid to vapor, right? You would look at the delta H of vaporization. How much energy does it take to turn a liquid into a vapor? Remember, this is an endothermic process. You have to add energy to turn a liquid into a gas. Likewise, if we're going in the opposite direction, we're going from vapor to liquid, we'd have to look at the delta H of condensation, right? That's the change of state that we're going through. Wow, that A looks really terrible. Okay, that makes it look even worse. Anyway, it doesn't matter. So going from vapor to liquid, we can look at the delta H of condensation. We can look at that value. How much energy will be released when you turn a gas into a liquid? So again, this is exothermic. So a little point to make off to the side here. The higher the boiling point, which I'll abbreviate BP, boiling point, the higher the boiling point, the stronger the forces. So we can look at the delta H of vaporizations for different substances and how much energy will it take to turn the liquid substance into its gaseous state. And whichever substance has the greatest delta H of vaporization, well then that means it has stronger forces. For example, if you're comparing 3 different molecules and they're all polar, well then that just tells you that the dipole-dipole attraction is the intermolecular force. And then you might be asked some question like, hey, which one has the greatest intermolecular force? Then you would compare something like, hey, you compare boiling points. Whichever has the higher boiling point, you have the stronger force. Whichever has the greatest delta H of vaporization has the stronger forces. Whichever has the greatest delta H of condensation has the greatest force, right? The more energy that it takes, all that energy is going in to break down those forces, right? When you boil something, you turn something from a liquid into a vapor. You're breaking down the intermolecular force. You're taking the attraction between the 2 liquid molecules and you're breaking it down so those liquid molecules aren't attracted to each other anymore and they separate. They get really, really far apart. Hey, that's our definition of a gas. Molecules really, really far apart. So keep those relationships in mind. I'm also going to add one other thing. This one's come up before. I'm going to kind of cram it in here in the bottom. Thing to take note of the saying, like dissolves like, which is kind of just the universal chemistry saying, meaning polar substances dissolve in other polar substances, right? The like dissolves like just means the same. Polar dissolves polar. Nonpolar dissolves nonpolar. But you really can't mix those two together. You can't take a nonpolar substance and mix it. I said nonpolar, right? You can't take a nonpolar substance and mix it together with a polar substance, right? They will not be attracted to each other. They will not form intermolecular forces between them. They won't mix together, okay? But if I take 2 different substances that are both polar, well, then if they're both polar, they both have a positive and negative end. I mix them all together, and they'll be attracted to each other. Likewise, if you take 2 nonpolar things, well, then there is no, or not that there's no, but there's very little positive and negative ends to the molecule, so they all kind of get along. All right, but trying to mix 2 different things together doesn't really happen. Nonpolar and polar don't mix. Okay, let's look at a specific kind of dipole-dipole attraction, kind of in its own category. This type of dipole-dipole attraction is called hydrogen bonding. I'm going to put in parentheses because the word bonding is actually kind of misused here. You can call it a hydrogen force, is actually a better term for it. But unfortunately, in the chemistry community, we still apply the term hydrogen bonding. So I still teach that even though it's kind of incorrect because it's not actually a bond. It's just a force. Okay. I forgot to underline. I like doing that. All right. So what's a hydrogen bond, you might be asking? It is the strongest type. Strongest type of dipole-dipole attraction. You have to have a polar molecule in order to have hydrogen bonding. But it is so specific, it's kind of in its own little category. So here's a very general point. Generally, BP, I'm using that one again, boiling points of related compounds increase with molar mass. So if I have two compounds that are generally related, the same, kind of made up of the same type of atoms, same type of bonds, things like that, the heavier one will have a greater boiling point, right? The heavier the molecule gets, the greater its boiling point gets. That's a pretty universal trend. Okay, larger molecules tend to, quote unquote, stick to each other. They tend to kind of have greater forces among each other. They're heavier, so it takes more energy to turn that liquid substance into a gaseous substance, right? To boil it. But some molecules break this trend, and we see and we see that in these examples. Things like H2O, hydrogen fluoride, and ammonia. They have much higher boiling points than we would expect. All three of these examples, their masses are very, very small. H2O is only 18 grams per mole. Hydrogen fluoride, what's that, about 20. Ammonia, NH3, that's only 17 grams per mole. Very, very small substances, but their boiling points are way higher than their masses would have you think. So you might be looking at them and thinking, what is in common with all of them? And they all have hydrogen in them. And of course, I already put this under the title of hydrogen bonding. So the reason they have very high boiling points is because they have hydrogen bonding. Okay. The key thing here, though, is not just hydrogen. You can't look at every single substance that has hydrogen bonding. No. It has to be specifically hydrogen bonded to nitrogen, hydrogen bonded to oxygen, or hydrogen bonded to fluorine. It has to be one of those three bonds within a molecule. The hydrogen has to be connected to one of those three. And the key thing here is the electronegativity difference. So these three atoms, fluorine, oxygen, and nitrogen, have pretty high electronegativities. Fluorine's at the top of the list. Oxygen's very high. Nitrogen's very high. We don't worry about any other ones. I know what you might be thinking. Chlorine. Chlorine also has a very high electronegativity, but does not lead to actual hydrogen bonding. So put that one out of your head. But when you have very high electronegativity in fluorine, oxygen, nitrogen, hydrogen being bonded to them gives you a really big electronegativity difference, which means the electrons are not shared very evenly, and so that leads to very, very polar molecules. In fact, they're so polar, they lead to much higher boiling points and much different properties than we would expect for molecules that are super, super light, like water, hydrogen fluoride, and ammonia. So electronegativity difference makes for very polar bonds. Okay, so again, it has to be that type of bond between, we have to have the bond between H and N, H and O, or H and F. Has to be one of those three. Okay. So again, we wouldn't just call any one a molecule that has this type of bond in it. We wouldn't just call it polar. We would say yes, it is polar, but we'd say it has hydrogen bonding or hydrogen forces. Okay. One easy way to remember those, the three elements. Hydrogen bonding is fun. Okay. Yeah. So it's kind of, like it's fun, but it's fun. F-O-N. You could say it's NOF. I don't know what that means, but you're more than welcome to use it. Often. That's even better. Hey, I think somebody said that last year. I don't really remember. Hydrogen bonding occurs often? I don't know. Make up your own. Fun usually works. People remember that one. That one's pretty stupid. But yes, be mindful that when you do have hydrogen connected to any one of these three atoms within a molecule, you have hydrogen bonding present. Okie dokie. All right, I was going to draw just a really simple diagram of the molecules, what's going on here. Okay, so for example, let's say, oh boy, that's my arrow. Sorry, I thought I had the marker. Come on. Okay, here we go. So I'm going to make this nice and big. So let's say we have here a molecule made up, yeah, whatever. Okay, one molecule there, one molecule here. So let's say these are two molecules of hydrogen fluoride. Let's keep it simple. So we have hydrogen, and fluorine. Okay, so two hydrogen fluoride molecules are near each other. We know that this is a polar bond. We know fluorine has a greater electronegativity, so this is partially negative, this is partially positive. And when these two molecules come near each other, they're going to line up in this fashion, right? The positive end of this molecule here, the hydrogen, will be attracted to the negative end of this HF molecule here. And what occurs in between them, oh, that's the stupid arrow again. This would be known as the hydrogen force, okay, or the hydrogen bond. Call it H bond. Like, my name is Bond. H bond. Okay, that's I don't do that very well. Okay, anyway, hydrogen bond or hydrogen force, but then you can't tell the bond joke, so I still tend to call it a hydrogen bond. But yeah, that's what's occurring. And so this occurs, trillions of times as you have lots and lots of molecules all near each other. That force is a hydrogen force. Very, very strong. HF has a much higher boiling point than we would expect for a molecule that's so light. Okay, so a super strong force leads to very, very high boiling points, high delta H of vaporization, delta H of condensation, all of the above. Good stuff. Okie dokie. One last force we need to go over. I'm going to start a new page. All right. The last force on our list are known as, actually they have a few names. They're known as dispersion forces. It's kind of the bottom of the barrel. This is the weakest of all forces, right? So these forces are found in all substances. Everything's got them. They're the weakest ones. Sometimes, some substances, this is the only force they have. It's super weak. Their boiling point will be extremely low. So on and so forth. We'll kind of go through all these different points. So this is the weakest. Some other terms I'm just going to put on here just in case you guys read about them in other sources and they start talking about something with another name. I don't want you to be confused. Sometimes we call them London forces. Another name that's even crazier, van der Waal forces. they all mean the exact same thing. Dispersion force, London force, or van der Waal force. All exactly the same. I tend to just stick with dispersion forces, but you're more than welcome to use any of the ones you want to. They're all still universally used, and like I said, you'll find them in different sources. Another thing I'm going to show you guys here in a few minutes, these types of forces involve induced dipoles. So this idea I'll show you is kind of how we take something that's nonpolar, but it can actually have a little bit of a polar moment to it. It's kind of neat. Alright, so let's kind of jump into it. Let's look at kind of an example of what I'm talking about. So let's say we have O2. And we have this fact, O2 can dissolve in water. So a little statement right there. Proven fact. We've tested it. It happens. But O2 is nonpolar, right? It's two oxygen atoms bonded together. That's like the quintessential nonpolar bond, right? Two of the exact same atoms with the exact same electronegativity. There will be no electronegativity difference. Totally nonpolar. So how can we... that's the word but, sorry. But O2 is nonpolar. So how on earth can something nonpolar dissolve in water, which we know is highly polar? Well, it leads to this idea. So we say here, water can, water can induce a dipole, I'll say in nonpolar molecules. Okay, so water we know is really, really polar. It can actually cause a polar moment. It can induce, right? Induce is the, I don't know, it's kind of one of those words, you kind of know the definition, you don't know how to explain it. Induce is kind of like force, right? Hey, my wife is going to be induced, I suppose. I don't know, she's really just getting a C-section. I don't think that's induced. But hey, women get induced into labor, right? Because they kind of get like forced or made to go into labor. Okay, I'm rambling. So you induce, you cause, you force a nonpolar molecule to actually become polar for a very, very small amount of time and just for like a short, quick instant. But hey, it happens. So I'm going to draw you guys an image here, so I'm going to go to a new page. Alright, so let's say we have our O2 molecule. O2 has our double bond, our lone pairs. There's our happy O2. Oxygen shares the electron cloud evenly, right? Totally nonpolar. Everything all spread nice and even. And let's say we dump O2 into water. Water, we know, is polar. So here's our oxygen atom and our hydrogens. So oxygen, we know, is partially negative. Hydrogens are partially positive. So it comes near the O2, and this negative charge here actually causes the electron cloud around the O2 to get shoved away and shifted. Right? The electrons we know are all negative. They are not going to be attracted to this negative charge here in water. So this negative charge on the oxygen in water is going to force the electrons away. It's going to repel them. Okay? So we're going to transition. As this occurs, our oxygen, which had everything in a nice balance, is not balanced anymore, and the electrons, I'm going to kind of draw them, the cloud, gets shifted, right? The electrons now exist more down here on this end as the water molecule approaches from the right. Oh, I got my arrow again. So here's our water molecule. Now our water molecule becomes a little bit more attracted now. It just caused a little bit of a positive charge here, just a little bit of a one. And hey, there's a little bit of an attraction there. And now with all the electrons getting shoved this way, this end becomes partially negative. Well, guess what? There's probably another water molecule somewhere nearby, and it's going to be attracted to this end as well, but not by the oxygen. It'll be attracted with the hydrogen ends because they're partially positive. That's supposed to be negative. And so you see this kind of creates like a rippling effect. And as it happens in one molecule, then this water molecule over here on the left gets attracted and then like attracts those electrons, and they get pulled even more because this is a little bit positive, and they get attracted here, and this kind of happens, it ricochets and happens in lots of molecules all at once. But of course everything is very dynamic, and this water molecule might get shoved around, moved, and it might go away, and then the electrons will snap back to this position where it's more of a nonpolar molecule. So moral of the story here, I guess I'll write it up. I'll just kind of explain it down here. Oh, got the arrow again. Oxygen in water causes, that's not how you spell imbalance, causes an imbalance of charge in O2. And this, of course, could have happened with the hydrogens in water too. I mean, I know I drew it with the oxygen up here coming into contact with the O2. It could have happened the other way around. The hydrogens could have come in contact and caused the same effect, right? But it's the idea that in something that's really, really polar, the charges are so they're just a lot stronger. The electronegativity difference is so much greater. The electrons are existing around oxygen so much more that they force a nonpolar molecule to act like it is polar. So this idea that we know that something nonpolar dissolves in something polar a little bit, okay, makes this idea possible. We still go with the like dissolves like saying, right? We say for the most part O2 not soluble in water, but some of it is. And this is how we explain that. This is how we rationalize it. Okay, let's wrap up some of these ideas. Okay. Oh, wrong color. All right, so I'm going to add one more thing to that diagram. Sorry. We say O2 has been induced. And this is called polarization. Okay, to make something that is nonpolar, we make it to be polar. Okay, polarization is to cause something to become polar. And that leads to this little idea, polarizability, which kind of like, as it sounds, ability to become polar. Our definition we apply is, it's the degree of distortion an atom or molecule can undergo. This idea is based on size. And we tend to use size, we tend to compare sizes on mass, right? Molar mass of different molecules, things like that. So polarizability, in layman's terms, it's a molecule's ability to become polar. So it's based on the size of the molecule. The rule is, the bigger your molecule, the more easily it is to be distorted. The electrons get moved around and shoved around on the molecule to where they aren't shared equally anymore. So the bigger the molecule, the more polarizable it is. Okay, so easily distorted, more polarizable. Polarizable. So really you just compare the molar masses of the different substances. If they give you 5 different substances and say, hey, which one's more polarizable, you just compare their masses. Add up all the molar masses, go with the largest one. Okay? And again, this all applies to non-polar molecules. Okay? So keep that in mind. Okay. Okay, one last point we got to make on this topic here, and then I'll kind of summarize everything up. We might ask the question, what about, that says about, what about two nonpolar molecules? Right? How can two nonpolar molecules actually have any force in between them? How can it have any electrostatic force if there's no charge on the molecule? Okay, so our answer is they do not have an overall charge, but momentary. I think that's how you spell that word, momentary. Momentary induced dipoles can happen. Cram that word down here. So momentary induced, right? Only for a split second can nonpolar molecules actually cause a polar moment to happen. But only for a moment. Okay, again, a majority of the molecules are all nonpolar, but every so often, between two or thousands of molecules, you'll get just a quick polar, little polar, teeny tiny polar moment. And I can draw an image of what's going on there on the next page. All right, so let's say we have, I'm just going to draw some general pictures here, two nonpolar molecules. Whoop. There you go. Two nonpolar molecules. I'm just drawing two circles. There we go. Doesn't matter what the molecule is. Electrons are all shared nice and even. Nice symmetrical shape. So here I'm just going to say average electron shape is a sphere. Yay. But we all know that electrons do not stay in one place. They move. They're constantly moving. All right. So as these electrons are flying all over the place, right? They're flying all over each of these molecules, like that, all over this one. At any given moment, maybe, just for a split second, more electrons might exist on one end of the molecule than the other one. And then, boom, you have a polar molecule. Right? If you have more electrons at one end than another, you have an imbalance of charge. And that might cause an imbalance of charge in another molecule, and this little chain reaction process occurs. So I'll try to draw what's going on there. So that perfect sphere shape, oh geez, I got the arrow again. That perfect sphere shape might become more like ovals. So this end might become negative, and this end might become positive, which would cause this end to become positive, and this end to become negative. So we all know electrons can move. That supposed to say move. Electrons can move, and that alters the electron density. The electrons are not distributed evenly anymore. And I suppose we can kind of wrap this up by drawing one more position. Those two ovals might line up perfectly, positive to negative, positive to negative. Okay? And the molecules realign. And this is more stable. You now have an electrostatic attraction between these two molecules. And this might keep going on and on and on and on, over trillions of molecules. But it's only for a moment, right? This might only happen for a split second, and then the molecules snap back to this position here, where they're just perfect spheres, and the electrons are all shared nice and even. And who knows, after a few more moments, this all might happen again, so on and so forth, and keep flying through that process over and over and over again. Okay, so this is how we kind of rationalize that a nonpolar molecule can actually have electrostatic attractions between the molecules. Okay, in order for a nonpolar molecule to become a liquid, this has to happen. Okay, tons of nonpolar molecules are liquids, and And in order for them to do that, there has to be an attraction between one molecule and another. They have to, quote unquote, stick together. Right? This is what causes that stick, this electrostatic attraction. Okay, those are intermolecular forces. Know them really, really well. I'm going to do one more thing for you guys that last year's class asked for. I'll kind of wrap up here in a second with it. One thing, though, I do want to add. In this chapter, you can get better images of these pictures I've drawn. I've kind of copied some of the ones from our textbook. There's a figure. Oh, jeez. There's a figure in our textbook in the chapter. It is on, it's figure 13.14, and it's on page 597. It kind of does a good job of summarizing all the different intermolecular forces and ranking them, and giving examples of molecules that have those intermolecular forces. Okay, so I think it does a pretty good job of just kind of laying it all right out there in a really simple, sort of easy to understand diagram. Okay, so take a look at that one. Even if intermolecular forces are making a lot of sense to you, look at that diagram. If that continues to make sense, great. Okay. One of the things you really got to get good at is looking at any molecule and sort of figuring out what's the dominating intermolecular force. Okay. My brain always starts with the weakest and then goes to the strongest. So the weakest is the dispersion. Actually, no, I lied. My brain, I like to go from strongest to the weakest. So one of the strongest ones was the ion dipole, right? So you see if there are ions present. Then you have to ask yourself, hey, is this molecule polar? If it is, great. Then you know dipole's involved. But then you also have to ask yourself, hey, is the hydrogen present? Is it HO, HN, HF? Then you know hydrogen bonding is the strongest. If the molecule is nonpolar, then the only answer is dispersion. Right? Nonpolar molecules, the only intermolecular force present is dispersion forces. So I'm going to kind of put this into a, I'm drawing a blank on what it's called. I'll probably remember it as I'm doing it. But I'm going to draw this out in kind of an easy-to-use diagram. Okay? So check this out. Okay, I'm going to try to fit this flow chart into one page. Let's kind of see how that goes. So here we just kind of have what I kind of developed, and actually I've seen this around after I made mine up. A lot of people use this. Kind of a series of questions to kind of get down to what is the predominant intermolecular force in a molecule. So the first thing you have to ask yourself, are ions present? Okay. That's your question. If the answer is yes, you go this way. If it's no, we're going this way. So if the answer is yes, you have to ask yourself this other little separate question then. You have to say, okay, are ions mixed with polar molecules? Okay. If the answer is yes, I probably should have used other colors. Oh well. If the answer is yes, then your major force is ion dipole. Because you have ions mixed with dipole polar molecules. If the answer is no, well then you should only just have ions, and guess what? Your ionic bonding, it's not really too much of an intermolecular force. But just checking that you have an ionic compound. Okay, again, much of which that we deal with intermolecular forces, we don't tend to do a lot with the ion dipole. Ionic bonding, that's more of an intramolecular force, right? The forces within a molecule. We've talked about ionic bonding already. What we're mainly going to deal with is kind of the answer to our first question, no's. We have to ask ourselves, if no ions are present, we have to check to see if the molecule is polar. So is the molecule polar? You ask yourself that question. Stretch down here. If the answer is yes, we have another question to ask. If the answer is simply no, well, guess what? Dispersion is your main force. Okay, if your molecule is polar, then you got to ask yourself this question: is H bonded to F, O, or N? Fluorine, oxygen, or nitrogen? If the answer is yes, then hydrogen force or a hydrogen bond is your main intermolecular force. If the answer is no, then you are simply a dipole intermolecular force keeping you together. And that's kind of how the flow chart works, to try to figure out what's the dominating intermolecular force. Okay, nonpolar molecules have dispersion. If you're polar, then you're dipole-dipole. Check to see if hydrogen bonding is present. If you're dealing with ions, ionic bonding might be your ultimate choice, but if it's mixed with some type of polar molecule, then you're ion-dipole. Okay. Let's see other things to add. So like I said, students sort of asked for something. They were kind of struggling last year with figuring out what's the dominating intermolecular force. So I came up with this, and then actually a few hours ago, I did some searches, and people have already done this. They've created diagrams of it. You guys can search for it. Just do intermolecular forces. You'll get tons of images, pictures, other videos, lots of other help. So please take advantage. The other thing you want to watch out for. So this kind of helps in figuring out what's the dominating intermolecular force. Some questions, be careful, like, read how they're worded. Sometimes they say list all forces, right? So it's kind of like a hierarchy type of thing. Depending on where you are in terms of strength, I suppose I can rank these. The strongest force that I have on here is ionic bonding. This is the strongest. Ion dipole, second strongest. Third, hydrogen bonding. Fourth, dipole-dipole, and the weakest, dispersion. So I suppose if some question like wanted you to list all forces present, if I have hydrogen bonding as the strongest, well, guess what? In order to have hydrogen bonding, you have to be polar, so you're dipole-dipole, and just about everything has dispersion, so that gets listed for everything. So it's kind of like starting with figuring out what the strongest is, and then listing everything below that. Would be the proper answer to that question. It doesn't come up very often, but I've seen it every now and then, maybe on older things. They might not ask it anymore. They just want to know what's the dominating intermolecular force, in which case you're only trying to figure out one. So this flowchart really helps. Get some practice, guys, identifying polarity in molecules, figuring out what's the predominating intermolecular force. We use it for the rest of the chapter, so get confident with it. Okay, good luck.
Made with Doodlecast Pro.